In continuation of discussion about the wave functions, in my last lecture, I have presented a comprehensive interpretation of this wave function and its acceptability or conditions of acceptability in quantum mechanical system. Today, in continuation of that lecture, I shall describe some properties associated with the wave function in quantum mechanics. The first property of this wave function, I can say the normalized wave function. Normalized wave function. We know that the modulus psi squared d tau is the probability of finding the system within this volume element d tau. If we consider the full range where the system is accessible, then this probability will be the summation, and it will summation, and as psi is continuous, so this will be the summation will be replaced by the integration, and here all space and this one equal to 1. If this condition is followed by this wave function, then we shall call this psi is a normalized wave function. If psi is not normalized, then it has to be normalized by multiplying a constant A called normalization constant. In such case, it will be all space and modulus A psi squared into d tau equal to 1. And automatically we already know if psi is a solution of the Schrödinger equation for a system, then A psi will also be a solution to the Schrödinger equation of that system. So in that case, A is constant, so it will be A square into integration all space and modulus psi squared d tau equal to 1, or A square equal to 1 by summation all space integration all space modulus psi squared d tau. By this way, the constant A, normalization constant, is being evaluated, and when A is multiplied with this psi, and this will give you the normalized wave function. So I can cite one example. Say particle in 1D box. Let the psi of this nth state is equal to a into sine n pi x by a, where a is the length of this box within which this particle is free to access or free to move, and a is the normalization constant. Then by putting this normalization condition, by putting these normalization conditions, we can get this value of a. Suppose here the limit will be 0 to L. This is the range of this particle to be available, and a square you can take it outside, and here the sine square n pi x by a into dx equal to 1. If we do these calculations, say a square by 2 into 0 to L and twice sine square n pi x by L dx equal to 1, or a square by 2 0 to L, this will be 1 minus cos twice n pi x by L into dx equal to 1. Or another step I can also do this a square by 2 integration 0 to L and dx minus a square by 2 into cos 2n pi x by L dx, and this equal to 1. Or this part, whenever it is integrated and put this limit 0 to L, this second part becomes 0, so it will be, this a will be equal to root of 2 by L. So the normalized wave function, in this case, the particle in one dimensional box, this normalization constant, this psi n, so psi normalized wave function becomes root of 2 by L sine n pi x by L. Another, I can give another example. Say 1s orbital of this hydrogen atom. The wave function of this 1s orbital is equal to, let n is the normalization constant, e to the power minus r by a naught. A naught is some constant which is called Bohr first orbit radius. R is the radial distance of this electron from the nucleus. So if we like to find the value of n, then it will be here all space. It is this electron is moving in 3D space, so all space 1s square into d tau equal to 1, but d tau equal to dx, dy and dz, a small volume element which is in polar coordinates r square dr sine theta and d theta and d phi. So putting here, we can get n square outside of this integral sign, and 0 r equal to 0 to infinity. This is the limit of this r, and this one equal to e to the power minus twice r by a naught into r square dr, and then integration theta 0 to pi and sine theta d theta and phi equal to 0 to twice pi and d phi equal to 1. Whenever we do this integration, here it could be integrated by using this gamma function. This one will be equal to 2 and this one 2 pi. And so putting all the values, doing this integration and putting this limit, this value of n will be equal to phi into a naught cube to the power minus a half. So whenever this normalization condition is put, a normalization constant is put here, the expressions of psi s, which is called the atomic orbitals, one is atomic orbitals, is pi a naught cube to the power minus half into e to the power minus half by a naught. So by this way, we can also do more calculations. I can set some other examples which are given to my students to exercise at home. This say psi n equal to a into e to the power n into cos n phi x by L over the range is minus L x plus L. If we do the same way as we have shown, this A will be found to be 1 by root over A. Another example I can also give that this is system having the wave function psi n equal to a into x into the power minus x square by 2 to within the range and x are varying minus infinity to plus infinity. If we do the same way, then a normalization constant is found to be 4 by pi to the power 1 by 4. Now I may come to this second property, orthogonal wave functions, and the two orthogonal wave function. Orthogonal wave functions. Whenever we solve the Schrödinger equation of a system, we can get the several solutions, several solutions of this psi and e. Suppose psi I is the wave function corresponding to its energy E1, and psi 2, the psi j will be another wave function for this system having this energy E2. E1 and E2, if they are not same, then the psi 1 or psi 2 are called non-degenerate. And psi 1 and psi 2 will be orthogonal if this is psi I and psi j and d tau all space becomes equal to 0. If this condition is being maintained, then we can call the psi I and psi j are orthogonal wave functions for this system. Orthogonal in geometry means perpendicular to each other. In that case, this E1 and E2 will never overlap to each other, and psi 1 and psi 2, they are also independent. One cannot be expressed in terms of this other. Some examples I can also cite for a particle in one-dimensional box, particle in 1D box. boundary box. Another one example I can give. Suppose this is the limit is 0 to L, as the box particle is within this 0 to L distance, and this is suppose psi I, psi j, and dx equal to, you shall have to find out the value whether this integration will give you the zero value. If it gives zero value, then these two are orthogonal to each other. Then 0 to L, and this case will be a square, say, and this one sin n I pi x by L, and sin n j pi x by L into dx. N I and n j, these are the quantum numbers for the two states in this system. If we do this integration, say a square by 2, and here 0 to L, and this 2 here also we shall give 2, and in that case in this case will be the cos n I minus n j into pi x by L, and minus a cos n I plus n j into phi x divided by L, and this is ds, whenever 2 is included, and turning into costs. So if we do this separate integration separately for this 2 and find out this result, then automatically this one comes equal to 0. That means psi I and psi j are orthogonal to each other. Then third property I can also give, this third one, this orthonormal wave functions. Orthonormal wave functions. In this case, both the functions should be normalized and also orthogonal. Both the conditions should be there. Suppose psi or space, we can write the first condition psi I and psi j and d tau equal to 1 when I is equal to j. This is the condition for normalization. Condition of normalization. Condition of normalization, and the second one, this psi or space and psi I and psi j d tau equal to 0 when n is not equal to j, and this is the condition for orthogonality. This is the condition for orthogonal. So these two, whenever we are coming jointly, we can write psi I, psi j or space. Actually, these indications are expressed in terms of Kronecker delta. Kronecker delta. This is beta. Delta, this indication is defined by Kronecker delta ij equal to 1 when I equal to j and equal to 0 when I is not equal to j. These two conditions are equal for the functions to be orthogonal wave functions. We can also give you the examples. Suppose psi psi equal to psi n equal to root over of 2 by L into sine n pi x by L is the wave functions or particularly in one-dimensional box, and we can see whether this psi n is psi n functions are orthonormal wave functions or not. Then we can have to put this condition and this condition separately, and whenever these two conditions are being obeyed, then we can say this wave functions for this particular in one-dimensional box are orthonormal. And this fourth one, the fourth property, and this one I can say last property, fourth one, degenerate. Degenerate wave functions. If it is possible that suppose psi 1 and psi 2, these two wave functions of a system is found to have the same energy and the same energy value, then we can call this psi 1 and psi 2 are degenerate wave functions. As we have seen in this in p orbitals, there are px, py, pz, but all these three p orbitals have the same energy value, so they are threefold degenerate. We can cite one example is that suppose in a hotel there are 3 or 5 or 7 rooms are there, rent of each room is equal, and amenities or facilities of this room, of all the rooms are same. Only the difference is that some are south facing, some is south facing, some is west facing, some is east facing, and orientation of these rooms are different. So these rooms are either threefold degenerate or fivefold degenerate or sevenfold degenerate, etc. In case of p orbitals also, in case of px, the electron lobe is oriented along this x-axis, py along the oriented y-axis, and pz lobes are oriented along this z-axis, but energetically they are same. This is all about this short lecture, all about these properties of these wave functions associated, and these are used in quantum mechanics very widely. Again, I thank you all who are watching this video, and if you like, then please subscribe.